You got a double, so you got a 6?
So you got 2.
You got 3.
All right. Let's take a look at this. Let's use trapezoidal rule to calculate a couple areas.
Why? What is he doing? What is he doing? He's a teacher. You can't just do that to a teacher. It's actually really good class. You can do it.
I've had a rough day.
Today?
And yesterday. I got shot yesterday.
A lot of people in my class got
Hey,
more people.
you probably just put that band-aid on.
Then I got a scratch right here.
Okay, there we go. Let's take a look at this. So if we want to use trapezoidal rule. All right, go coach those throwers up. If we're going to use trapezoidal rule to approximate this area, right? All we do. This is very similar to the stuff we did earlier with rectangles, only easier. It's not as complicated. We just have to take this specific information. See it, and take the specific information and apply it to the general trapezoidal rule. Does anybody remember what that is? What's the area? See if you can do it without notes. B minus A over 2n. Right, instead of n, it's 2n out front times the quantity f of, there you go.
Well, what's your recycle bin?
You have a recycle bin?
I do. It's back over here. It got moved.
Do you know
Of course I have a recycle
Do you know organs like one that recycles?
I would believe that. It's generally in a pretty close state. There you go.
Vietnam.
Gosh, let's keep doing that.
Good.
Okay, there it is, right? If we're only doing a limited number, you can write it that way. When we start to write big numbers of trapezoids, then you don't want to write it this way. Then you want to use that sigma notation. Here it's, 6 of 1, half a dozen of the other. So we've got our multiplier b minus a over 2n times f of x of 0, which is really just f of a, right? Plus 2 times f of x of 1, plus 2 times f of x of 2, plus 2 times f of x of 3, plus f of x of 4, which is really just b, f of b, right? To find out what all those interior, what are these guys, x of 1 and x of 2, etc., we know that x sub I is just equal always to a plus I delta x, right? Okay, so for us, if we're going from 0 to 2, the width of the interval is 2, 2 minus 0, divided by 4 trapezoids, gives us delta x equals 2 over 4, or 1/2, right? Just like before. Okay. And so this looks like, x sub I just looks like 0 plus I times 1/2 is just I over 2, right? So then x sub 1 would just be 1/2, x sub 2 would be 2/2 or 1, x sub 3 would be 3/2, and finally x sub 4 is 2, b, has to be, right? Okay, and so for this function then, for f of x equals x squared, if we plug all this stuff in, what do we get? We get an area, so b minus a we said was 2, n was 4, so 2n is 8. Right? So 2/8 is the multiplier out front, times f of 0. Well, what is f of 0? 0. Sure. So I'm just going to get 0 squared, which is 0, plus 2 times f of x sub 1. Well, that's 1/2, right? We're just moving over in increments of 1/2. So that's 0, 1/2, 1, 3/2, and 2. So what's f of 1/2? Well, 1/2 squared, right? Okay. Plus f of 1, right? 1 squared, right? Plus, yeah, f of 3/2 is 3/2 squared, plus 2 squared. Add it up, and that's our answer, right? It's going to give us back a number. It's not going to be perfect, but it's going to be an approximation. So we get, if we do quickly add that up, 1/4 times 0 plus 2 times 1/4 is 1/2, right? Plus 2 plus 9/4 times 2 would be 9/2. Plus 2 squared is 4. And 9/2 and 1/2 is 10/2, so that's 5, and 6 is 11, so 11/4. We add all that up. Okay. So that's our trapezoidal rule approximation. Now that would have changed if it had been bigger than that. Is it any good? How do we know? Here's how we know. Okay, the error associated with the trapezoidal rule. There's a formula for this. If we want to know what the error is with the trapezoidal rule approximation, here's what we do. It's the quantity b minus a cubed over 12n squared times something kind of goofy. The maximum of the absolute value of the second derivative on our interval. Okay. Okay, so pretty straightforward except for that one piece. We know b, we know a, we know n. So finding that fraction's simple. This is the part that's a little strange. Okay, what's the maximum value of the absolute value of the second derivative on our interval? Okay, and that's the part that can be a little tricky. But what this is going to give me then, this is going to give me the worst possible outcome. In other words, if I let's find out what we got here. Okay, let's find out what our maximum error was in this previous calculation. So if we plug in this stuff, b minus a was, we say 2 cubed is 8 over 12 times 4 squared times this stuff, right? Well, the function was x squared, right? So if f of x is x squared, what's f prime of x? 2x. What's f double prime of x? So what's the absolute value
2.
of f double prime of x?
Absolute value.
Yeah, it's 2 and it's constant. It's not changing. So then it doesn't matter what the interval is. The maximum value anywhere for the absolute value of the second derivative is 2 in this case, right? So if we plug that in, we get this number times 2. What is that? 16 over 12 is 4/3. So 4 over 3 times 16, 4 squared. So that gives us 4 on the bottom of 1/12. Did I do that right? Yep.
What if second derivative isn't as nice as it is?
We'll do one where it's not as nice. Yeah. We'll look at one where it's not. Then we have to actually look at it a little more closely, right? We'll look at one like that here soon. So that's the most our calculation was off by. So if we need to be closer than within 1/12, what must we do in our trapezoidal rule approximation? Say it again. Use more trapezoids. Right? If that's close enough, we're there. Right? So keep in mind, this is never going to give us a perfect answer. This is, by its very nature, this is numerical approximation. Yeah.
On assignment, are you going to have a specific number of trapezoids?
Ah, okay.
Or I
Well,
understand
what I'm going to do, what I'm actually going to do is something more like this. What I'm going to say on the assignment, here's how a problem like this really works. Let's take, what's a good one out of the assignment here? Something like this guy, okay? Okay. Here's one. We want to approximate the integral of 1 over x, definite integral of 1 over x, dx from 1 to 3. Okay, now here's what we got to do. We need our error to be less than or equal to, actually just less than, we're going to say. It needs to be less than 0.00001. Okay? So that's going to tell us how many trapezoids we have to use at minimum. Okay? How is that going to tell us? Well, because there's f of x, right? We know a is 1. We know b is 3.
How do we find that?
And we're going to find n from that error formula. We're just going to solve for n in that error formula, right? Let's go ahead and calculate the second derivative real quick. What's f of x? Prime of x, sorry. Negative 2. Okay, and so f double prime
I'm
of
kind of
x.
confused with how we can find it.
Okay, you'll see.
In
You'll see.
general.
Well, then this is how. That we're doing one right now. Before we can do this problem, if we want to approximate this with less than that much error, that's going to dictate the number of trapezoids we need to use. And once we know the number of trapezoids, we'll just plug into the trapezoidal rule formula and have done with it. Okay, but how do we find the number? Well, we're going to have to take that formula, right? This formula right here. And we're going to evaluate, well, we're going to solve for n, right? We're going to set our limit to be 0.000001. And we know everything else. We can calculate this quantity, right? Because we know the function. We know a and b, so we'll just solve for n, given those parameters, and see what the minimum number of trapezoids must be, and then we'll use that number. Okay? So, what's our second derivative? Which is 2 over x cubed. So on our interval then, on the interval from 1 to 3, wouldn't you agree that where we've got positive values of x, the absolute value isn't going to change this, right? So I'm going to write that. So for the closed interval from 1 to 3, the absolute value of the second derivative is just that, right? So I'm putting positive numbers in there. I'm getting positive results. Agreed? Okay. Where is it going to be a minimum? Now explore the behavior of this function here. If the x is on the bottom, to make the overall fraction the smallest, what do I want to do to the bottom of the fraction? Make it the biggest, right? So we could say then, and this is literally how you'll say this. You just say by inspection. And what we're really inspecting is the denominator, right? By inspection, we know that the maximum value, we're looking for maximum value, not minimum. The maximum value would have to be where? If we minimize this fraction when the bottom is big, we maximize it when the bottom is small, right? So the maximum value of this weird animal on this interval has to occur at 1, where the bottom is the smallest. Small denominator equals big fraction, right? And so then we can come up with an actual value for that. The maximum of the absolute value of f double prime of x is equal to 2 over 1 cubed. It's 2. Okay? Does that make sense?
Yeah.
Okay? And, we could graph that, but we don't need to. That's a pretty easy one to see. So then we've got that ingredient, right? We know A, we know B. Now let's just go back to our formula. Okay, so we can find out the error approximation here. We know that expression we had was B minus A cubed over 12n squared times that thing, right? That whole thing, that's our error, has to be less than 0.00001, right? That's our allowable error. So if we plug in all the particulars, 3 minus 1 is 2, right? See where we're going with this? So that becomes a 2. On the bottom we get 12n squared, and then this whole thing right here just became 2, exactly. Right? Now we're getting it, okay? So if we simplify this, let's see, we get 2 cubed times 2 is 2 to the 4, so that's 16?
Yeah.
So 16 over 12 would be 4/3. So 4 over 3n squared is less than 0.00001. Right? Now what do we do to get that to solve for n squared there? Here's a tricky step. Gotta be a little careful with that. But what can we do with a ratio like this? The n's on the bottom, unfortunately. I need it on the top. Okay, we can flip both sides. But here's something you haven't done often if you've done it at all. We had some rules about inequalities going way back to probably Algebra 1. Remember we said if we multiply or divide by a negative, we got to flip the sign? Okay, but we also have to flip the sign if we inherently change if we reciprocate both sides. Because, does that make sense? Because fractions have inverse behaviors with regard to the numerator and denominator. If I flip them, right, a big denominator makes a small fraction, but a big numerator makes a big fraction, right? So when we flip these things then, let me just grab this and go to the next page. Okay, so then when we flip this guy, I'm going to get 3n squared over 4 is greater than 1 over 0.00001. Now I can turn that, what is that really? If I move the decimal 1, 2, 3, 4, 5 places on the bottom to get a 1, what do I do on the top? That's the same thing as multiplying the bottom by 10, 100, 1,000, 10,000, 100,000. Exactly. Move the decimal point the same number on the top. So I could, if I wanted to, I could just trade this guy out. Does that make sense? I could trade this guy out for a 1, 2, 3, 4, 5. There's my decimal. Well, there's my decimal. 1, 2, 3, 4, 5. Just add 5 zeros, right? Make sense? I don't have to. I can put it in my calculator that way if I want to, though. I don't have to do any of that. I could. Let's undo it. It's because we can't. Whoops. Okay, so we could have moved everything. Either way, though, to solve for n squared, what do we end up doing? Now it's the same kind of stuff we've done in the past. Now what do we do to isolate an n squared? Okay, so good. So multiply by 4/3. So n squared is greater than 4 over 0.00003, right? If I multiply by 3. And then if I square root both sides, I get n is greater than 2 over the square root of 0.00003, or even just the square root of the whole thing. That's fine. Okay, so if we put that in our calculator, What do we get back?
Wait, why didn't you just rewrite the whole thing?
We could. Square root of that whole thing. Square root of 4 divided by point.
Never mind. I got it, never mind.
Okay, here's what I get back. I get back an answer of then n is greater than 365.148, blah, blah, blah. Okay?
Yeah.
So here's a critical question then. What's n?
166.
Greater than a U.
366, yeah. Because n is a discrete number of trapezoids, and if it has to be bigger than 365 and change, it's got to be at least 366, right? You have to take the next biggest discrete value, and we overshot a little bit, but better safe than sorry. Now we know for a fact that our answer is going to be within our tolerance of 0.00001, right?
We have to use 366.
So we have to use 366 trapezoids to get that to work. Now clearly that's not one we're going to do manually,
So
is it?
depending on which way the arrow is, will go.
Depending on, say it again?
Which way the inequality is facing.
Right, but it'll always be up. It'll always be up because if you're calculating a number of trapezoids, the math gods wouldn't have it any other way, because to have it be less than would mean I could pick 0, right? Does that make sense? So it has to be a greater than.
Can we go up to the very top?
Yep.
Why can't you just, on the very first blue, or not the black, like the original one, why can't you just switch the denominator and the numerator of the opposite sides of the equation?
Well, you can, but you can. That's essentially what we did. But then you gotta. It's easier to remember. Do you flip the signs or not? Then you know you.
You don't, because you're multiplying both sides. You're not doing anything with the negative. I'm talking about putting the 0.0001 on the bottom and then just having the 3 and squared on the other side.
That's what we did.
Oh, then why do you have to flip the sign?
Well.
That way you don't have to flip the sign.
I mean, you still do, because when you're pulling the variable to the other side, then you're flipping the sign. Now the sign relative to the variable has changed. You got to be careful with those, though. You can do that in this case. I would advise against that, because later on there are some instances where you can't do that, and you don't want to get in the habit. I don't know. I've done this stuff a ton. I wouldn't do that. I would reciprocate both sides and solve for n. Okay.
It's a good thing we have you, right?
Well, I mean, that's just what the book would tell you, too. It's no big deal. So now we got n, right? We'll just go back and figure out. Now we got to plug it in. But this is a different example. This time we can't do it manually. We're just going to add it up using sigma stuff, right? So what was our original problem? What was 1 over x? Is that what?
I have absolutely no idea.
Isn't that like
1 over x. There's the original, right?
Wait, wait.
So we know what n is. Let me rewrite that. So here's the area we're trying to approximate. And it was 1 to 3? 1 to 3, right? Is approximately what? Okay. 366, right? We know that n has to be 366. Okay, so now let's go back and let's write the kind of the revamped sigma-friendly version of the trapezoidal rule. So. Oh. Yeah, 1 to 3. Yeah. Okay, so now we've got our b minus a over 2n times f of 1, right? I mean, I should write it in terms of a. Let me write it in terms of a. F of a plus f of b plus 2 times the interior sum, right? The sum of f of x of I, which is just going to be a plus I delta x from I equals 1 up to what? Okay, yeah, but in general, is it n?
Yeah.
No.
N minus 1.
N minus 1. Good. It's the interior sum, right? We're not going to take the 0th or the nth. We're only taking the inside ones from 1 to n minus 1, right? Okay. Now we'll plug the stuff in and get an answer. And you'll see this is no big deal. This is really not hard to do. So b is 3, so let's plug everything in. 3 minus 1 over 2 times 266, 366. Times f of 0 is just, f of 1, sorry. F of 1 is 1, right? Plus f of 3 would be 1/3. Plus 2 times the sum of f of...
Is there something on your calculator?
There's what?
Something, some symbols?
Yeah, there is. There is. On the new operating system, it actually, instead of having to do sum of sequence like you used to, now it actually gives you a nice looking little sigma. You just fill in all the buttons. Yeah, it's nice. So the sum of f of 1 plus, what's delta x going to be? If n is 366, what's delta x? It's always b minus a over 2n, right?
B minus A over 2n.
Right, so what is it for us then? B minus a would be what? Width of the interval.
Oh, 2
2. Okay.
over n, which is 2 over 366.
2 over 366, which reduces to, I guess, to what? 1 over
100. Wait.
176? No. What's 168?
It's 1 oh. Don't you have to flip it around?
188. What now?
Don't you have to, isn't it 366 over 2?
This is where you said delta x was 2 over 2, right?
No. That's out here. This is a 2n.
Oh, okay.
Delta x, same as it always was. Just b minus a over n. Width of the interval divided by the number of trapezoids. So it's got to be tiny, right? Delta x is going to be really small.
Yeah.
The width of the trapezoids.
But it's 1 over x. So you have to flip it.
But that doesn't have anything to do with delta x. Delta x, all delta x is, remember, here, let's go calculate delta x down here. So delta x, delta x is always the same. That's never changed. Delta x is just the width of the interval divided by the number of subintervals, right? Nothing to do with the function. Just the width divided by how many times we slice in it. So we get 2 over 366, which is 1 over 183, right? Did I do that right? Yeah, okay. So then we know that delta x is 1/183rd, so we can plug that in right here, right? So we get 1 plus I times 1 over 183, just I over 183. There's our function that we're going to add up from 1 to 365, right? Now, what is f of, maybe this is what you're asking, what is f of all that stuff? 1 over all that stuff, right? F of x is 1 over x, so f of hand is 1 over hand, right? So this is what we're actually going to put into our calculators then. We're going to put in 2, that's a 2 that cancels with that 2, right? Yeah. So we just get 1 over 366. 1 plus 1/3 is just 4/3. Okay, we can do that part by hand. Plus 2 times the sum of 1 over 1 plus I over 183 as I runs from 1 to 365. So let's do that on our calculators. And then we can just verify, we can actually ask the calculator to give us a really good approximation, and we'll just verify that we got within our tolerance. Okay, so we got 1 over 366 okay, times this big quantity, 4/3, right? 4/3 plus 2 times, and now I got to move. 2 times all that stuff, right? So how do we put that in? Everybody agrees that part's correct, right?
Yep.
So we got to fill in this sigma. So that's where we go math,
I feel like before the over is going to be 3 plus 2.
and then 0, right? We just hit 0 for summation. And then look at that, isn't that cool? So we get the whole template there. So we're gonna let our variable, might as well let it be x, right? Instead of I, we'll call it x. X goes from 1 to 365. And what is it we're summing? That stuff. Question. I could. It wouldn't hurt, but I don't need them.
Yeah, I think it might be like 3 plus.
So it might be like 3 plus. That's what I was thinking, Dave, 3 plus.
Well, okay, but the calculator knows order of operation, so it's going to know that it's going to do division before.
But doesn't know the 4/3 is a fraction rather than 4
It doesn't matter.
rather than 4 divided by 3.
It doesn't make any difference because 4 divided by 3 or 4/3, either way, when it does order of operations, it's going to execute that division first. And so 4 divided by 3 is 4/3.
Yeah.
We'll see. Just to check.
Yeah, we'll see.
Yeah, but I understand. You could always play it safe. I guarantee I won't need to though.
My calculator puts it like all under the fraction.
Puts it all under the fraction.
Yeah,
Okay.
4 and then everything else behind it.
Okay. Now, if we're using the fraction template.
No.
Oh, strange. Well, I want to see if it messes up. I don't think it will, but I'm kind of curious if it does. We can check and see if it does. So then, we got to put this stuff then inside the sigma. There's the argument of this stuff. There's the argument of the sigma, right? So it's 1 divided by. Now this time I will definitely need it in parentheses. 1 divided by the quantity.
Just use the little tool.
I could.
Here's the one.
You want me to?
Yeah, do it.
Yeah.
Alpha,
Okay.
Y.
Now you're gonna throw me off.
Okay, I'll do that. Thanks, Andy.
What do you do?
I'm going to use my little. How do I get to that? It's
Alpha, go alpha, then go the little graph to Y equals,
alpha y
and
equals.
then 1.
Oh, there it is. Yeah, that's right. I remember.
Yeah, I don't have it on my
Okay, so that's supposed to be, I got to get rid of this guy. Darn it. Okay, so there's a 1, right? Divided by 1 plus, I got to do it again. 1 plus x is my I, divided by 163.
Or 183.
183. You're right. Can't read my own writing. 183. Okay, and that should be it. Okay, that's it, right? Yeah, it is. And then I got to close the parentheses around the whole thing, I believe. I don't think I did that yet. Okay. So let me just scroll back so we can see the whole thing, just to make sure. The sigma part looks good. Come on.
Faster than Saber, man.
Brett Wagner to the office. Brett Wagner to the office.
Okay, that's good, right? Because I got my 1,366 times that whole thing then. So let's try it. You have to think probably a little bit. That's a big sum.
It's thinking.
It's a lot to do for a little calculator.
It's not a real calculator.
It's going to take an hour.
It's gonna kill your computer.
It's going to take a little while.
Offering.
It's gonna crash your computer.
Do yours go faster than this?
Yeah.
My computer? Yeah. My computer goes.
Do your calculators
Yeah.
faster than this emulator?
Oh, did it?
Yours is done?
No, it's
No.
done.
Oh, it did? Okay, so there it is. Now let's check and see. Let's see if that's how accurate that really is. Now, of course, this is just going to be an approximation, but this will be a good souped-up approximation using the calculator's fancy algorithms.
Without a calculator.
Oh, this one we could. You're right. This one we could do. This one will be exact. So if we go math, what was it? Is it what number? I forget what number. 9.
What about
Math 9. We're adding from 1 to 3 the function 1 over x
So find the area under the curve.
under that curve, right? And we get an answer of, what do you know? Okay. Did we hit our accuracy? Are we within .00001? Yes, we are.
And then
Out
right
to
after
5
this,
places, we get the same digit. How about that? Okay. That, my friends, is big
Wait, so why
time.
did we do all the work for?
Because we had to find out the number of trapezoids to use. Now watch what would happen. I'll prove my point. If we go back up to this original, let's go back up here to our calculation, and let's let the number of trapezoids be, what if it had only been, instead of being 366, what if it had been 20? Okay, that would have changed. Oops, darn it, go down there. Well, I just have to read the whole thing.
No, no,
I gotta grab it. That would have changed this to, changed a bunch of things, right? It would have changed this to a 10 on the bottom, because that was half of 366, right? So that would have been 10. Okay, and then what else would we have changed? Yeah, then that went out in front, and that's it, huh? Oh, then with that 365 would have been a 19, right? So 193, okay. And then the multiplier would have been 1 over 20, right? Okay, and now watch what happens. When we calculate that one, we don't get, it's not accurate enough. See, that one did not take, we needed to go up to .00001, and then we fell long short of that. 20 wouldn't have been enough, so we had to know how many trapezoids did we want to calculate. And there's a practical matter here. Why didn't we just pick a billion and call it good? Well, how long would that have taken for the calculator to do that? Yeah, it would have crashed it. It couldn't have done it. So you want to pick the smallest number you can for the computation that's still going to get the job done. So that's where that first part came in. Right? That's pretty cool, don't you think?
Yeah.
All right, and like I mentioned yesterday, real calculators don't use the trapezoidal rule because it's too inefficient. You have to add up too many things. They would use a more aggressive, instead of picking trapezoidal tops, linear tops to those sections, they would pick a more aggressive fit that would be probably quadratic or cubic. It's probably not even polynomial. It's probably something really different. But then they'd have to do fewer calculations, but the individual calculations would just be nastier. And so you just gotta walk that road and see where's the best place. It would have been in the past. It probably, well, I don't know. I think now with really high-speed chips, you probably could do trapezoidal rule and add it up a ton of times, and it would still work pretty easily. If you use like the i7s that are so good at doing just linear calculations. If the clock speed is really high, if it's over 4.
Overclock it.
Yeah, I mean you can overclock it even then. If you're running at over 4 gigahertz, then that's really fast. And so you can do all these repetitive calculations, easy calculations, and get an answer pretty easily. What?
They run that 2.2, and they just overclock it and figure it out.
Well, but there are faster versions of the i7 now.
Are there?
Oh yeah.
Like, what's the fastest?